All right, it is 3 o'clock, so let's start. Just one announcement before we get started. Everybody knows that registration for the summer and fall is coming up really soon. If you haven't made an appointment to see whoever your advisor is, you should do that soon so that you can sign up for summer and fall classes. Those that have been here for a year or more know that summer classes fill up really rapidly, right? So it's important that you do that early as opposed to waiting if you need to take anything this summer. Okay? Fair enough? Just a reminder, because sign up for classes starts next Wednesday, the 8th. Okay? All right, we're going to finish chapter 10. All we have left to do is talk about buffers. We're not going to spend a lot of time on it. We're not going to do any calculations with buffers. And then we're going to start on chapter 8. So we're going to go back to gases. Okay? And when we do gases, we're going to actually go outside and do a little activity so that you guys can understand how gases work a little bit. You like that idea?
Yes.
Okay. So we'll do that in a minute. First, let's talk about buffers. I don't like the wording on this slide. I see y'all sitting there writing feverishly. It says, buffer solutions maintain the pH by neutralizing small amounts of acid and base. I don't like the word neutralizing. I would prefer reacting with. Because when a lot of people think about buffers, they think that, oh, well, a buffer means that a solution is going to go to pH 7. Because pH 7 is neutral, right?
Yeah.
Nothing could be further from the truth. I can make a buffer at any pH I want. A really common buffer is made with acetic acid and sodium acetate. It's got pH of about 4.3. Okay? Buffers do not have to be neutral. They can be any range of pHs. What is true, though, is that a buffer resists pH changing by reacting with small amounts of acid and base. So if I have water and I add acid, what happens to the pH? If I just have water and I add an acid, what happens to the pH? It goes down. Acid is low pH, right? If I add a base, what happens to it? It goes up. But when you have a buffer and you add a small amount of acid, what happens to the pH? It changes a little bit. Or if you add a base, it changes a little bit. It's important for certain reactions, like in your blood, to carry the right amount of oxygen. It's important that your blood pH remain about 7.35. That's not neutral, is it? It's slightly basic. And your blood is buffered so that your red blood cells will work, right? The ocean is buffered as well. It's buffered at about 8.2. That's not neutral, okay? But it is buffered, so that small things don't affect the pH, okay? Now, and that's what we just said. So buffers work because they resist pH change because of how you make them up. And the way you make a buffer is you have to start with a weak acid, and then you also have to add a whole bunch of the conjugate base. Notice, in this example, we have acetic acid, and on the right-hand side we have the acetate ion. How do we know that this is the conjugate base for this weak acid? How do we know that this is the conjugate base for this weak acid? What's different between here and here?
The H.
The H is gone. So somewhere over here, there's an H plus, right? This is different than this by one H. That's what makes it a conjugate acid-base pair. And so the way to make this would be to take and add a whole bunch of that, and also add a whole bunch of sodium acetate or potassium acetate. Okay? So you add the weak acid and the salt of the conjugate base. Right? This is a salt. So, in a buffer system like that one, we can have both the salt, right, and the weak acid. Now, what happens when you add acid or base to the system is the question. Well, if I add acid to the system, what happens? Think about it. Remember this right here? It's a two-way street, right? So if I add more stuff on this side, it makes this reaction come over here. If I add more stuff on this side, it makes it go over there. So when you add acid or base, it's capable of responding and not changing the concentrations a great amount. Okay? And that's, I like their little graph. They went through each of these. So if we start here in the middle with equal amounts of weak acid and conjugate base, if I add a little bit of acid, it responds so that it makes a little bit more of the weak acid, but we still have a whole bunch of the conjugate base. If I add some base, it makes a little bit more of the conjugate base, but we still have a whole bunch of the acid. So the concentrations aren't changing so much. It's not like if we just add hydronium ions and there's nothing there for it to react with and the pH goes way down. It reacts and prevents the pH from changing dramatically. Okay? So the question is are any of these ones up here a buffer? And we're going to do them one at a time and talk about them. So, how did we say you had to make a buffer? You have to have a weak acid and the conjugate base there, okay? Is A buffer? Do we have a weak acid there in A? Huh? You think we do? Where's the weak acid? HCl is a strong acid. It's one of the 6 strong acids. You cannot make a buffer with a strong acid. Okay. So this is a strong acid, so nope, that's not a buffer system. All right, what about this one?
Weak.
This is a weak acid right here, yes? Is this the conjugate base with a cation?
Hold on.
Well, let's figure it out. What would the conjugate base of this acid be? What does it mean to be a conjugate base? It means it's lost what? A hydrogen. So HCO3 minus would be the conjugate base, right? What if we just take, whoops. What if we just take that negative sign off and just add a sodium on here like this? Because all that really means is that these two are attracted to each other, right? So these two come together to give me this. Okay? Does everybody see that? Megan's shaking her head. No. Do you understand this is the conjugate base? And then this is just some cation that happens to be floating around. And he's attracted to the conjugate base, so he just hangs on because negative and positive are attracted. And that makes this the salt of the conjugate base. Okay? This could be anything. It could be potassium, it could be lithium, it could be any cation. Okay? What about this one? Is it a buffer system? All right, you say yes. Explain yourself why you say yes.
So it's a weak acid.
It is a weak acid.
Sodium chloride's got to be strong. It's not on there, but.
That's phosphoric acid. It is a weak acid. Is that the conjugate base there in the salt?
No, it's not.
It is not. That is a salt, right? But it's not the salt of the conjugate base, is it? You got to have the conjugate base there. So that's not a buffer, is it?
So what is it? Nothing.
Nothing. It's salty phosphoric acid, I guess. I don't know. Y'all know phosphoric acid's what they put in soft drinks, right? They put carbonate, they pressurize it with CO2, and that makes carbonic acid, but they also put phosphoric acid in it too. There's lots of acid in soda. All right, what about D? Is it a buffer system?
Yes.
It is a weak acid. What acid is that? That's acetic acid, okay? Is that the conjugate base? Is that a salt of the conjugate base then?
Yes.
Yes, it is. Because the conjugate base of this would be what? C2H3O2 minus, right?
Yes.
And then we just say that, oh, we have potassium hanging on, so that's the same thing right here, okay? So yes, this is a buffer, and this is a buffer. A and C are not buffered. And that's the end of chapter 10. That's all, folks. Now,
Can you do one thing?
sure. So you calculator lesson? Can we do that after class?
Yeah.
We're gonna start on chapter 8, so don't go anywhere. All right, we're gonna go outside in a few minutes, but first we gotta explain some stuff first, okay? First one is P is pressure. V is, N is number of moles.
How's that? Temperature?
T is temperature. Okay? All right, let's explain what each one of them is. What is pressure? Pressure is how many times you hit the wall and how hard you hit the wall. Okay? Fair enough? How hard and how many times? So, for example, if I bump into this wall right here and I'm going real slow, there's not a lot of pressure. But if I'm going real fast, boom, give myself a concussion, right?
Yes.
Okay? So pressure is related to how fast you're going, okay, and how many times you hit it. I can hit it 10 times really slow, and the pressure is the same as if I hit it one time really hard. Okay? That's important. Okay? Volume is how big of an area you are in. How big a space do you take up? Number of moles, self-explanatory, right? How much stuff do you have? And in temperature, what's temperature related to?
Motion.
Heat, kinetic energy, right? The more kinetic energy, the more heat you have, the faster you're moving. So remember those things, okay?